Imagine standing on the edge of the universe, gazing out into the boundless expanse. Beyond the stars, galaxies, and nebulae lies a profound enigma, the origin of everything. The universe we know today, vast, expanding, and filled with galaxies, stars, and planets, began in an unimaginable moment of creation. This moment, known as the Big Bang, marks the birth of everything: space, time, matter, and energy. But what if the Big Bang wasn't the start of everything? What if it was the manifestation of something far older and more mysterious? Could the Big Bang itself have been the first white hole? The Big Bang theory suggests that the universe began as a singularity, an infinitely dense point where all matter and energy were compressed. From this tiny, dense point, the universe expanded rapidly, creating everything we see today. It's a compelling idea, one that explains many aspects of the universe's current state, such as its expansion and the cosmic microwave background radiation. However, this narrative leaves us with a question: what caused the Big Bang? Was it a one-time event, or could it have been part of a larger, cyclical process? This question becomes even more intriguing when we turn our attention to the concept of white holes. While black holes are well-known cosmic phenomena, white holes remain a theoretical concept. They are imagined as the opposite of black holes, regions of space-time that expel matter and energy rather than sucking it in. In other words, if black holes trap everything that crosses their event horizon, white holes would expel everything, never allowing anything to enter. What if the Big Bang was, in essence, the birth of our universe from a white hole? If we consider that black holes and white holes are two sides of the same coin, then could the Big Bang have been a white hole expelling matter into an empty, unknown cosmos? This thought-provoking idea challenges our conventional understanding of cosmology and suggests that the universe might not have simply begun out of nowhere. It could have been birthed from something else entirely, from a cosmic event that expelled the universe into existence. As we embark on this journey through space and time, let us explore the possibility that the Big Bang was not the first event, but the latest manifestation of a far more ancient and mysterious process. What if the universe itself is part of an eternal cycle, and the Big Bang is just one chapter in a never-ending story? Take a moment to reflect on this. What do you think lies beyond the horizon of our understanding? White holes are one of the most puzzling and fascinating theoretical concepts in modern physics. To understand them, it's helpful to first think about their counterparts, black holes. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. They are created when massive stars collapse under their own gravity, pulling everything inward into a singularity, a point where space and time become infinitely warped. However, while black holes are well documented and observed, white holes remain entirely theoretical, existing only in the equations of general relativity. In essence, a white hole is imagined to be the opposite of a black hole. While black holes trap everything that enters them, white holes are thought to expel matter and energy. If you were to approach a white hole, rather than being sucked in, you would be repelled. Anything that crosses the event horizon of a white hole cannot return. The very idea challenges our intuitive understanding of how objects in the universe interact with one another. Instead of pulling everything in, white holes push things out, releasing matter, radiation, and energy into the universe. But why, you might ask, should we care about something so strange and theoretical? The concept of white holes is not just a curiosity of physics. It could hold profound implications for how we understand the universe's origins. If the Big Bang was indeed the creation of our universe, could it have been a white hole event? The Big Bang was a moment of rapid expansion, where all matter and energy burst out into the vast emptiness of space. Could this have been the action of a white hole, a cosmic phenomenon that expelled the contents of a previous universe, leading to the formation of our own? White holes, if they exist, could be the key to understanding the fundamental nature of the universe. They might provide insights into the structure of space-time itself, particularly in relation to black holes. In fact, some physicists speculate that the singularities inside black holes could actually be connected to white holes. Perhaps, when a black hole reaches the end of its life, it might give birth to a white hole, releasing all the matter it has consumed back into the universe in an explosive event, possibly even triggering a new Big Bang. Take a moment to reflect on this idea. Could the universe we live in today have been the result of such an extraordinary event? Could white holes be the key to unlocking the ultimate mystery of the cosmos? Space-time is not just a backdrop for the universe. It is the very fabric of reality itself, shaping and being shaped by the objects within it. Imagine a rubber sheet stretched out with a heavy ball placed in the center. The sheet curves under the weight of the ball, creating a well that distorts the space around it. This is an analogy for how mass and energy bend space-time. In Einstein's theory of general relativity, space-time is described as a four-dimensional continuum, 3 dimensions of space, length, width, and height, and one of time. When massive objects like stars, planets, or black holes are present, they warp space-time, creating gravitational fields that affect everything within them. This curvature of space-time is what we perceive as gravity. The concept of space-time is mind-bending because it goes against our everyday experience of the universe. We usually think of space and time as separate entities, with time moving forward relentlessly, and space being a stable container for everything that exists. But Einstein's breakthrough was to show that space and time are intertwined. One cannot exist without the other. This realization forms the foundation of modern cosmology and our understanding of the universe's structure. Now let's tie this back to white holes and the Big Bang. The curvature of space-time becomes especially important when we consider extreme phenomena like black holes and white holes. A black hole forms when a massive star collapses inward under its own gravity, creating a singularity, an infinitely dense point at the center where space-time becomes infinitely curved. In this scenario, space-time itself is stretched and distorted so severely that nothing can escape its pull, not even light. But what happens when the curvature of space-time works in the opposite direction, causing matter and energy to be expelled rather than pulled in? This is where the idea of white holes comes into play. If a black hole is a point where space-time curves inward to a singularity, could a white hole be a point where space-time curves outward? Could the birth of our universe, the Big Bang, have been the result of an extreme warping of space-time, a cosmic explosion of energy expelled from a white hole? In this view, the Big Bang was not just the birth of matter, but the moment space-time itself stretched outward, creating the universe. Take a moment to reflect on the implications of this. Space-time is not just a passive stage for the events of the universe. It actively shapes the course of cosmic history. Could the birth of the universe itself be tied to a profound and dramatic distortion of space-time? If so, what does this say about the very nature of existence? And how does this understanding of space-time fit into the broader mystery of white holes and the origin of everything we know? At the most fundamental level of reality, things behave in a way that defies common sense. This is the world of quantum mechanics, where particles act unpredictably, exist in multiple states at once, and seemingly defy the rules of classical physics. Quantum mechanics governs the smallest scales of matter, from the tiniest subatomic particles like electrons and photons, to the forces that govern their behavior. In the quantum realm, the certainty of the macroscopic world gives way to uncertainty, and where time and space are no longer fixed and unchanging but can bend, fluctuate, and warp in unexpected ways. Perhaps the most perplexing concept in quantum mechanics is the idea of quantum fluctuations. Tiny, momentary changes in energy that occur in empty space. These fluctuations are the result of the inherent uncertainty built into the quantum world. On the subatomic scale, particles appear and disappear in the blink of an eye, even in what seems to be empty space. These fluctuations could be the source of the raw energy that drives the creation of matter, and in some theories, they might even play a crucial role in the formation of black holes and, more intriguingly, white holes. Now, consider this. What if the Big Bang, the very birth of our universe, was the result of a quantum fluctuation? In the vacuum of space, Particles pop in and out of existence constantly, and according to some speculative theories, a sufficiently large fluctuation could have caused the universe to emerge from nothing. Imagine a brief moment where energy and matter spontaneously appeared from this fluctuation, eventually growing and expanding into the vast universe we know today. This idea ties into the concept of quantum foam, where even the fabric of space-time itself is not smooth, but constantly fluctuating at incredibly small scales. If quantum mechanics allows for the creation of particles from nothing, could it also explain how white holes might operate? Just as quantum fluctuations can cause particles to appear out of the void, could white holes be the result of such fluctuations in space-time? Instead of pulling everything in, like black holes, white holes might expel matter and energy from these very fluctuations, creating entire universes in the process. The idea that a quantum fluctuation could not only trigger the birth of our universe, but also create the conditions for a white hole opens up a radical new way of thinking about cosmic creation. As you contemplate this possibility, think about how the quantum world, so distant from our everyday experiences, might be directly linked to the birth of the universe itself. Could the mysteries of quantum mechanics, its uncertainties and fluctuations, be the key to unlocking the secrets of white holes and the very origins of space and time? Reflect on the deep connection between the smallest building blocks of reality and the largest questions we face about the cosmos. In the early moments of the universe, something remarkable happened. Something so strange and counterintuitive that it has become one of the central mysteries of cosmology. During the first few moments after the Big Bang, the universe expanded at an incredibly rapid rate, far faster than the speed of light. This period of rapid expansion is known as cosmic inflation. It lasted for only a fraction of a second, but it fundamentally shaped the universe we see today. The paradox, however, lies in the nature of this expansion. How could the universe have expanded so quickly when nothing can travel faster than the speed of light, according to Einstein's theory of relativity? To understand cosmic inflation, it's important to recognize that it wasn't the matter and energy in the universe that was expanding faster than light. Rather, it was space itself that was stretching, causing galaxies to move away from each other at extraordinary speeds. During this brief period, the universe's size increased exponentially, from smaller than a quantum particle to something that could hold all the matter we observe today. But this expansion raises profound questions. How could such a rapid expansion be possible, and what caused it? The answer lies in the energy that filled the universe in the very early moments of existence. According to inflationary theory, the universe was filled with a type of energy known as the inflaton field. This field drove the rapid expansion of space, acting almost like a balloon being inflated. As space expanded, it cooled and allowed the matter and radiation that followed to form the universe's familiar structures. The theory explains many features of the universe, such as its uniformity and isotropy, the same in every direction, which would have been nearly impossible to explain without this inflationary period. However, there is an intriguing thought that comes out of this. Could the very rapid expansion of the universe during inflation have been linked to a white hole event? If a white hole is a phenomenon that expels energy and matter into the universe, could the sudden burst of space itself have been triggered by a similar event? Some theorists propose that the Big Bang could have been the birth of a white hole, which released not only matter, but the very fabric of space-time itself. The rapid expansion of the universe could have been the result of this violent expulsion, setting the stage for everything that followed. Take a moment to reflect on this. If inflation, in its extraordinary speed and magnitude, is tied to a white hole, then the origins of our universe might not have been as random or isolated as we once believed. Could the white hole hypothesis offer a new way of understanding the rapid birth of space and time itself? What implications does this have for the future of the universe and the mysteries that still lie ahead? The universe operates on a set of mathematical principles that describe everything from the motion of planets to the behavior of light and matter at the smallest scales. These mathematical equations don't just explain how things work, they reveal the underlying structure of reality itself. In the search for understanding the cosmos, these equations are our guiding tools. One of the most profound discoveries in the history of physics is how these equations, specifically Einstein's field equations of general relativity, describe the behavior of space-time. They explain how mass and energy warp the fabric of space-time, and how this warping leads to the formation of phenomena like black holes and, perhaps, white holes. Einstein's equations describe the relationship between matter, energy, and the curvature of space-time. They can be written as a set of intricate mathematical relationships that govern the dynamics of the universe. This is the mathematics that shapes the motion of planets, the flow of light, and even the expansion of the universe itself. Yet, these same equations suggest the possibility of extreme and puzzling phenomena that don't fit neatly into our everyday understanding of the universe, such as black holes and white holes. Black holes are perhaps the most well-known prediction of Einstein's equations. These objects form when a massive star collapses under its own gravity, creating a singularity at the center, a point where space-time becomes infinitely curved. The equations predict that anything that crosses the event horizon of a black hole will be trapped, unable to escape. But the equations also predict something equally curious: the existence of white holes. These theoretical objects are the inverse of black holes. They expel matter and energy instead of trapping it. However, unlike black holes, no white hole has ever been observed. So, why do these solutions exist in the equations of general relativity? Are they simply mathematical curiosities, or do they represent something real, waiting to be discovered? The very fact that white holes appear as a solution to Einstein's equations implies that they could, in theory, exist under the right conditions. Some theorists suggest that the Big Bang itself could be explained as the birth of a white hole. If the equations that describe black holes apply to white holes as well, then the rapid expansion of the universe during the Big Bang could have been a result of a white hole's explosion, spewing matter and energy into the universe in a manner consistent with what we observe. Take a moment to consider the implications of this. The mathematics that describes the universe is not just a tool for prediction. It could offer us glimpses into the fundamental structure of reality. Could these equations, which so perfectly describe black holes, also unlock the mysteries of white holes? Could the universe's birth be mathematically encoded in the very fabric of space-time, waiting for us to decode it? Reflect on how these elegant and complex equations might hold the answers to questions that have puzzled humanity for centuries. Time. This seemingly simple concept governs every moment of our lives, ticking away relentlessly, always moving forward. But when we step back and look at the universe on a grand scale, time becomes much more than a steady march. It becomes one of the most enigmatic aspects of the cosmos. Time is intertwined with the very fabric of space-time itself, and understanding its nature is essential to unlocking some of the greatest mysteries of the universe, including the Big Bang and the possible existence of white holes. In Einstein's theory of general relativity, time is not a constant, unchanging flow. It is deeply affected by gravity. Just as space-time can bend under the influence of mass and energy, so too can time slow down or speed up, depending on the curvature of space-time. This phenomenon is known as gravitational time dilation, and it means that time moves more slowly in stronger gravitational fields. For example, a clock placed near a massive object, like a black hole, would tick slower than one far from such an object. Time, in this sense, is not absolute. It is malleable, influenced by the very structure of space-time. This flexible nature of time becomes particularly important when we consider extreme conditions, such as those near black holes or during the Big Bang. The birth of the universe is thought to have occurred from a singularity, a point where space-time itself was infinitely curved, and both time and space became distorted. The Big Bang was not simply a point in time, but rather the beginning of time itself. Before this event, time, as we understand it, did not exist. The concept of before the Big Bang is meaningless because time itself began at that very moment. But what about white holes? If they exist, they too might be tied to the very fabric of time. A white hole is theorized to be an object that expels matter and energy rather than pulling it in like a black hole. Could a white hole operate as a time portal, releasing not just matter, but also information about the past or future? Some theories suggest that a white hole might represent a reversal of time, a process where the flow of time itself is reversed in some way, expelling the contents of a collapsing universe or a black hole into a new one. Take a moment to reflect on this. If time is not absolute, but instead deeply tied to the fabric of space-time, then could white holes be the key to understanding time itself? Could they offer a glimpse into a universe where time works differently, perhaps even in reverse? This opens up fascinating possibilities about the nature of time. Is it truly linear, or is it something far more fluid and unpredictable? Could the Big Bang, the birth of time, be part of an eternal cycle of time, where the flow of the universe constantly shifts in ways we are only beginning to understand? Time itself may be the greatest puzzle of all, and the discovery of white holes could be the key to unraveling it. The idea of a cyclical universe is as old as human curiosity about the cosmos, yet it remains one of the most compelling and mystifying concepts in cosmology. What if the universe we observe today is not the first, and certainly will not be the last? What if the birth of the universe, encapsulated in the Big Bang, is just one chapter in a long, repeating cycle of creation and destruction? This idea, known as the cyclic model, or eternal recurrence, challenges our conventional understanding of the universe's beginning and end, offering a radically different perspective on the nature of time itself. In the cyclic universe model, the universe undergoes a never-ending series of expansions and contractions. After the universe expands to a certain point, spreading galaxies apart, stars burning out, and entropy increasing, it begins to contract again under its own gravity. This contraction, known as the Big Crunch, would eventually lead to a state of immense density, much like the state of the universe before the Big Bang. Then, just as the universe reached its critical point, it would undergo another Big Bang, initiating a new phase of expansion. This cycle of birth, death, and rebirth would repeat endlessly, with no true beginning or end. The cyclic model raises fascinating questions about the ultimate fate of our universe. If the universe is truly cyclical, does this imply that every Big Bang is simply the latest in a long series of cosmic births? Each universe might be a reincarnation of the one before, with each cycle offering new possibilities and variations, but always following the same fundamental pattern. In this view, the Big Bang isn't a unique event, but just one link in a chain of cosmic events stretching back infinitely. Now, if white holes are real, they could play a central role in this cyclical process. In the context of the cyclic universe model, a white hole could represent the beginning of each new cycle. Just as black holes are thought to absorb all matter and energy, possibly leading to the formation of a singularity, white holes might expel that energy into a new, expanding universe. Each cycle of the universe's birth and death could, in this view, be triggered by the explosive event of a white hole, a cosmic birth that gives rise to a new universe with its own laws of physics, stars, and galaxies. Take a moment to reflect on this. If the universe is part of an infinite cycle of rebirth, how does that affect our understanding of time, of existence itself? The idea that the universe we know is just one iteration of many forces us to rethink the very nature of creation. Is the Big Bang merely the beginning of a single chapter, or is it part of a cosmic novel that has been unfolding for eternity? Could each of us, each moment of our lives, be part of a grand cosmic cycle that repeats endlessly across the vast stretches of time? The answers to these questions remain elusive, but the idea of a cyclical universe invites us to view the cosmos in an entirely new light. Imagine for a moment that the universe you see, this vast cosmos of stars, galaxies, and dark matter, is not the only one. What if the Big Bang, the event that created our universe, was just one of countless others, each spawning a separate universe with its own unique laws of physics and realities? This is the essence of the multiverse theory, one of the most fascinating and mind-boggling ideas in modern cosmology. The multiverse proposes that our universe is not alone. Instead, it is just one of many, potentially infinite universes that together form a multiverse. The concept of the multiverse has its roots in several different theories in physics. One of the most well-known is inflationary cosmology, which builds on the idea of cosmic inflation. According to inflation theory, the universe underwent an exponential expansion in its very early moments, stretching from smaller than a quantum particle to a vast, observable space in a fraction of a second. Some versions of inflationary theory suggest that this rapid expansion might not have been a singular event, but rather a process that repeats across different regions of space. In this framework, new pocket universes could continuously form within a much larger, inflating cosmos, each with its own distinct characteristics and physical laws. This means that while our universe is governed by certain constants, like the speed of light or the gravitational constant, other universes could have entirely different rules of nature. The implications of the multiverse theory are profound. It challenges our traditional view of the cosmos as a singular, unique creation, and suggests that there may be other realities that are just as valid, though entirely different from ours. Some versions of the multiverse even speculate that there could be universes where the laws of physics are so different that life, as we understand it, might not even be possible. The existence of multiple universes opens up questions about the nature of reality itself. Are we living in a universe where the conditions were just right for life to emerge, or could there be universes where conditions are completely inhospitable to life? Could the Big Bang be an event that links multiple universes rather than the start of just one? In the context of the multiverse, our universe may have originated from a white hole, a powerful burst of energy expelled from another universe. If every Big Bang is the beginning of a new universe within an ever-expanding multiverse, then perhaps our universe is just one of many created by this process. The idea that the Big Bang could have been the birth of not just our universe but one in an endless series of universes raises fascinating questions about the nature of existence and the true scope of reality. Take a moment to consider the possibility of the multiverse. Could the Big Bang be a doorway to infinite other universes, each with its own version of reality? What does it mean for us to think of our universe as just one of many, each existing in its own pocket of space and time? The multiverse theory invites us to think about our place in the cosmos in ways that challenge everything we know about the universe and the nature of reality itself. The search for new and unknown phenomena in the universe is one of the most exciting and challenging pursuits in modern science. While much of our understanding of the cosmos is grounded in established theories and observations, there are still countless mysteries that await discovery. One of the most elusive and speculative of these mysteries is the existence of white holes, cosmic objects that, if they exist, would defy everything we know about the behavior of matter and energy in the universe. But how could we detect something that has never been observed? Could there be a way to find these theoretical objects hidden among the stars? White holes are, in many ways, the inverse of black holes. While black holes suck in everything that crosses their event horizon, white holes are theorized to expel matter and energy, preventing anything from entering. Their very nature makes them incredibly difficult to detect, as they would not emit the same kinds of radiation or signals that black holes do. Black holes, for instance, can be observed through the X-rays emitted by matter as it falls toward them, as well as by the way their gravity bends light. In contrast, white holes would not have any matter falling toward them, so they would not produce the same detectable signals. Yet, some physicists believe that white holes could still leave subtle signs of their existence in the cosmos. One potential clue could lie in the way certain cosmic events unfold. If a white hole were to expel matter and energy into space, it could create bursts of radiation or high-energy particles, possibly detectable by space telescopes. These bursts might not last long, perhaps just moments or minutes, but if detected, they could be the signature of a white hole's activity. The difficulty lies in distinguishing these fleeting signals from the background noise of the universe. Another potential clue comes from the study of black holes themselves. Some scientists have suggested that black holes could be connected to white holes in a more direct way. The theory is that when matter is sucked into a black hole, it might eventually be expelled by a white hole, possibly in a different region of space or even in a different universe. If this idea proves to be true, it could provide an indirect way of detecting white holes by studying the behavior of black holes and the matter they contain. For example, if the contents of a black hole were suddenly ejected in an unusual burst, it might be evidence of a white hole's presence somewhere in the cosmos. As we continue to observe the universe with more powerful telescopes and advanced instruments, the search for white holes will likely remain one of the most intriguing quests in cosmology. Could these theoretical objects really exist, hidden in the far reaches of space, awaiting discovery? Could the detection of a white hole change our understanding of the universe and its origins forever? Take a moment to reflect on the vastness of space and the possibilities that still lie out there, waiting for us to uncover. The answers, perhaps, are closer than we think. While much of our attention in cosmology is directed toward the birth of the universe, the Big Bang, equally profound questions revolve around its eventual end. The fate of the universe has been a topic of speculation and theory for centuries. What will become of this vast cosmos after billions of years? Will it continue to expand indefinitely, or will it eventually collapse in on itself? Could the concept of a white hole somehow play a role in the universe's death and subsequent rebirth? The future of the universe is largely tied to its expansion, and scientists have developed a few theories to explain its potential end. One widely discussed theory is the Big Freeze, which proposes that as the universe continues to expand, it will eventually reach a point where all stars burn out, galaxies drift apart, and the cosmos becomes a cold, dark void. In this scenario, as stars and galaxies are increasingly separated by vast distances, the universe becomes more and more inhospitable to life. Energy will become scarce, and the cosmos will reach a state of maximum entropy, where no useful work can be performed, and everything is uniformly cold and devoid of structure. However, there are other theories, such as the Big Crunch, which proposes that the universe's expansion will eventually slow and reverse. Under the influence of gravity, all the matter in the universe would collapse inward, eventually leading to a singularity, a point of infinite density and temperature, much like the state of the universe before the Big Bang. If the Big Crunch is the end of one cycle, it raises an interesting question. Could this collapse lead to the birth of a new universe, initiated by a white hole? The idea of a white hole expelling matter and energy into a new universe suggests that it might act as a catalyst for the cosmos's rebirth. In this scenario, the end of the universe, the Big Crunch, could trigger a white hole's explosion, expelling all the accumulated matter and energy into a fresh, expanding universe. This would mark not the end of existence, but rather a transition to a new phase of cosmic history, with all the matter of the collapsed universe being recycled in a new Big Bang. If white holes exist, they could be central to this cyclical process of cosmic creation and destruction. Take a moment to reflect on this possibility. The universe's death, in this view, would not be an ultimate end, but rather a doorway to a new beginning. Could white holes be the cosmic gateways that allow for eternal renewal, creating an endless cycle of expansion and contraction? If this is true, it would mean that the universe, in some form, has no true beginning or end. Instead, it is part of a continuous loop of cosmic life and death. The more we explore these ideas, the more we realize that our understanding of the universe's end may be just as mysterious as its beginning. Entropy is a concept that governs much of the universe, and yet it is often one of the most difficult to grasp. In simple terms, entropy is a measure of disorder or randomness within a system. The second law of thermodynamics states that in any closed system, entropy will always increase over time, meaning that systems tend to move from a state of order to a state of disorder. The implications of this law are profound. It suggests that, left unchecked, the universe is gradually heading toward a state of maximum disorder, a condition often referred to as heat death. In such a state, everything in the universe would be evenly distributed and no useful energy would remain. The universe would be cold, dark, and devoid of the structures that make it what it is today: stars, galaxies, and even life itself. Yet, when we look at the universe as a whole, we observe something quite the opposite of what entropy suggests. The universe is filled with stars, galaxies, and complex structures that seem to defy the increasing disorder implied by entropy. Life, too, exists in highly organized systems, from cells to organisms to entire ecosystems. The very existence of life seems to run counter to the notion of entropy increasing, as living organisms maintain an extraordinary degree of order by consuming energy and expelling waste. This paradox becomes even more perplexing when we consider the birth of the universe itself, the Big Bang. In the moment of its creation, the universe was in an extremely low entropy state. Everything, space, time, and all the matter that would later form stars and galaxies, was condensed into a hot, dense singularity. How is it possible that such a highly ordered state could emerge from what is effectively a state of absolute chaos? The Big Bang's apparent contradiction with the law of entropy challenges our understanding of how the universe began and how it might evolve. Now, consider the possibility of white holes. If white holes are the counterparts to black holes, expelling matter and energy rather than absorbing it, could they represent a cosmic mechanism that resets entropy? Could a white hole, in its dramatic release of energy, be a process that counteracts the natural tendency toward disorder? In this view, the creation of a universe from a white hole might be a reset, a reduction of entropy that allows for the creation of a new, low-entropy universe, much like the one we observe today. This idea brings us back to the cyclical model of the universe, where each new Big Bang could represent a fresh start, a new phase in an ongoing cycle of cosmic rebirth. In each cycle, entropy might be reset, allowing for the emergence of structure and complexity once again. If this model holds, then the increasing entropy we observe in the universe today might not be the final word on the cosmos's fate. Instead, it could be part of a larger cosmic rhythm, one that involves periodic resets, where entropy is pushed back and the universe is born anew. Take a moment to reflect on this. The universe, as we understand it, is in a constant state of flux, moving toward disorder, yet bursting with order and complexity. Could white holes be the missing piece in understanding how the universe remains capable of generating new life and new structure despite the constant pull of entropy? This paradox challenges us to rethink the very nature of time, creation, and the ultimate fate of the cosmos. In the realm of physics, the laws of energy and mass conservation are fundamental principles that govern the behavior of everything in the universe. The law of conservation of energy states that energy cannot be created or destroyed. It can only change forms, transferring from one system to another. Similarly, the Sakis law of conservation of mass dictates that mass is neither created nor destroyed in any physical process. These laws seem to be absolute, applying universally to everything from the smallest subatomic particles to the largest galactic phenomena. But what happens when these laws are stretched to their limits in the extreme environments of black holes, white holes, and the very origins of the universe? In the case of black holes, the concept of conservation is put to the test. When matter falls into a black hole, it seems to disappear from the observable universe. This has led to the so-called information paradox, where the fundamental question arises: if matter and information are lost in a black hole, does this violate the laws of conservation? According to quantum mechanics, information cannot be destroyed, yet it appears to be lost once it crosses the event horizon of a black hole. This contradiction between general relativity and quantum mechanics is one of the greatest unsolved mysteries in modern physics. If black holes represent a breakdown in the conservation of information, could white holes somehow provide a solution to this conundrum? White holes, if they exist, might offer a way of conserving the mass and energy absorbed by black holes. While black holes suck in everything, including light, white holes are theorized to do the opposite, expelling matter and energy. In this sense, a white hole could represent the opposite of the information paradox. Rather than information being lost forever, it might be released into the universe from a white hole, restoring the energy and mass that were seemingly consumed by a black hole. This would mean that the conservation of energy and mass is preserved, but in a way that transcends the limitations of black holes. Now, consider the Big Bang itself. If the universe was born from a singularity, a point of infinite density, did the conservation laws apply in this scenario? The Big Bang is often considered the birth of both space and time, making it difficult to apply traditional notions of conservation. However, if the universe's formation was triggered by a white hole, this event might be a way of reconciling the creation of mass and energy from nothing. Could the laws of conservation be preserved not just in our universe, but across cycles of cosmic creation? If white holes expel energy and matter from a previous universe, as some theories suggest, then the principles of conservation might be operating on a universal scale, with each new Big Bang representing the beginning of a new cycle, where mass and energy are continually recycled. Take a moment to think about the implications. Could the very existence of white holes provide a deeper understanding of how the laws of conservation work on the grandest scales of the universe? If these principles are upheld through the cyclical processes of cosmic birth and death, then perhaps they are not limited to the confines of a single universe, but extend across an infinite cosmos. What does this mean for the way we understand the universe's past and future? Could energy and mass never truly be destroyed, merely transformed across the vast stretches of time and space? This idea invites us to reconsider not just the fate of the universe, but the very nature of conservation itself. Most of the universe remains invisible to our eyes, and yet it accounts for the vast majority of the cosmos. About 85% of the universe's mass is in the form of dark matter, and roughly 70% of the energy in the universe is attributed to dark energy. These two mysterious forces, which we cannot directly observe, are responsible for shaping the large-scale structure of the universe, influencing the motion of galaxies, and driving the accelerated expansion of space. The curious thing is that we have no idea what they are or how they interact with normal matter. But what if these dark forces, particularly dark energy, play a role in the phenomenon of white holes, and could even help explain the origins and fate of the universe? Let's begin with dark matter. Though invisible, we can infer its existence because of the way galaxies behave. Observations show that galaxies rotate much faster than their visible mass can account for, suggesting that there is some unseen mass providing additional gravitational pull. This invisible matter doesn't emit, absorb, or reflect light, making it extremely difficult to detect. Its influence, however, is crucial in holding galaxies together and affecting the overall structure of the universe. If white holes exist, could they be a mechanism through which dark matter is released into the universe? Perhaps white holes could act as sources of dark matter, expelling it into the cosmos, contributing to the unseen mass that shapes the gravitational interactions between galaxies. Then there is dark energy, an even more perplexing force. Dark energy is thought to be responsible for the accelerated expansion of the universe, causing galaxies to move apart at an ever-increasing rate. This force is counteracting the gravitational pull of matter, causing the expansion of space itself to speed up. While we cannot detect dark energy directly, its effects are measurable through the way galaxies move and how the universe is expanding. Some scientists speculate that dark energy could be related to the very fabric of space-time itself, providing the push that drives the expansion of the universe. Could white holes be somehow linked to dark energy, possibly acting as sources that expel energy into the universe, contributing to this mysterious force? If white holes are indeed real, they might provide the missing link between dark matter, dark energy, and the cosmic expansion we observe. the energy expelled by white holes could contribute to the accelerated expansion of the universe, much like the effects of dark energy. This could mean that white holes are not just theoretical curiosities, but might be fundamental to the very dynamics of the universe, helping to explain how dark energy works and how it influences the expansion of space. Take a moment to reflect on the vastness of these dark forces. Though we cannot see them directly, they shape everything we know about the universe. Could white holes, as sources of energy and matter, provide the key to understanding the most elusive components of the cosmos? The dark forces of the universe may be far more interconnected with the phenomenon of white holes than we realize, and exploring these connections could lead to an entirely new understanding of the universe's structure and future. As humans, we have always felt a deep connection to the universe, even though its vastness often leaves us feeling small and insignificant. From the earliest civilizations, people looked to the stars and the heavens, seeking meaning and understanding. The night sky has been a canvas for our curiosity, guiding explorers, inspiring philosophers, and shaping our sense of wonder. But as we look deeper into the cosmos, particularly with concepts like the Big Bang and white holes, we are faced with questions not just about the physical nature of the universe, but about our place within it. What is our relationship to these cosmic phenomena, and how do they reflect our quest for knowledge and meaning? Throughout history, human beings have sought to understand their environment and the forces that shape it. The development of science, from ancient astronomy to modern astrophysics, represents a continuing effort to uncover the secrets of the universe. In many ways, the study of the cosmos has been a search for something greater than ourselves, an attempt to comprehend the mysteries of existence. The Big Bang, the beginning of time and space itself, is a powerful concept that offers us a glimpse into the origins of everything we know. It challenges us to think beyond our everyday experiences and confronts us with the fact that the universe is far older, more expansive, and more mysterious than we can fully grasp. Similarly, the concept of white holes forces us to confront the limits of our knowledge. While black holes are well documented and studied, white holes remain a theoretical concept, one that exists only in the equations of general relativity. The possibility of white holes raises profound philosophical questions about the nature of existence. Could these cosmic objects, which expel matter and energy, be tied to the origins of the universe itself? And if so, what does that mean for our understanding of creation, time, and the universe's ultimate fate? As we venture into the unknown, we are not just exploring the cosmos, but also exploring ourselves. Our curiosity about the universe is a reflection of our desire to understand the deeper truths of existence. We are, in a way, part of this great cosmic narrative. Just as stars are born, live, and eventually die, so too are we caught in the cycle of creation and decay. The same forces that govern the birth and death of galaxies, stars, and planets also shape the lives of individuals, communities, and civilizations. Our search for meaning in the universe is, in a sense, a search for meaning in our own lives. Take a moment to reflect on this connection. The more we learn about the universe, the more we realize how deeply intertwined we are with it. The mysteries of the cosmos, whether the Big Bang, white holes, or the fundamental nature of time, are not just abstract concepts. They are part of our own journey, as we seek to understand our place in the vast, ever-expanding universe. What is it about our nature that compels us to look up at the stars, to ask these profound questions, and to seek answers? Perhaps in our quest to understand the cosmos, we are also searching for answers to our own existence. Black holes and white holes are often considered to be two sides of the same cosmic coin, two phenomena that stand in stark contrast to each other. Black holes are the well-known regions of space-time, where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon. They form when massive stars collapse under their own gravity, creating a singularity, an infinitely dense point where the laws of physics, as we know them, break down. The theory behind black holes has been well established through both mathematical models and observations, particularly the detection of gravitational waves and the study of the motion of stars near them. However, the concept of white holes, their opposite counterparts, remains largely theoretical, with no direct evidence to support their existence. If black holes are regions where space and time curve inward, trapping everything that falls in, white holes are imagined to be the opposite, regions where space and time curve outward, ejecting matter and energy. In theory, nothing can enter a white hole, just as nothing can escape a black hole. While black holes suck in matter from their surroundings, a white hole would expel matter, potentially creating bursts of energy or matter into the universe. This theoretical symmetry between black holes and white holes leads some to wonder, could these two cosmic phenomena be more closely connected than we think? The connection between black holes and white holes may lie in the fundamental structure of space-time itself. One idea is that the singularity at the center of a black hole, the point where space and time break down, might be connected to the singularity at the center of a white hole. Some theories even suggest that black holes could be connected to white holes through wormholes, theoretical passages through space-time that could allow for the transfer of matter from one region of the universe to another. These wormholes, if they exist, could potentially link a black hole in one region of the universe to a white hole in another. In this model, matter and energy could fall into a black hole, only to be expelled at the other end of the wormhole through a white hole, possibly in a distant part of the universe or even in a different universe altogether. This symmetry between black holes and white holes challenges our understanding of cosmic processes. If white holes do exist, could they be responsible for the creation of new matter, or even the birth of new universes? In the context of the cyclic model of the universe, a white hole might serve as the beginning of each new cycle, expelling matter and energy from a previous collapsed universe. In this view, each Big Bang might not be a one-time event, but rather the result of the ejection of energy and matter from a white hole, creating a fresh new cosmos. Take a moment to reflect on the profound implications of this. If black holes and white holes are truly connected, could the universe itself be engaged in an eternal process of recycling? The connection between the two might not just offer insight into how black holes operate, but also provide a deeper understanding of the universe's creation, its continual evolution, and perhaps even its eventual demise. Could the future of the universe lie in the cosmic symbiosis of these twin entities, black holes and white holes, forever exchanging matter and energy in a grand cosmic cycle? The concept of time travel has fascinated humanity for centuries, from ancient myths and legends to modern science fiction. The idea of traveling through time, whether to visit the past, witness future events, or even alter the course of history, has sparked the imagination of countless thinkers and dreamers. Time, as we understand it, seems to flow in one direction, from the past to the present and into the future. However, in the strange, mind-bending world of theoretical physics, time itself becomes a more fluid concept. And in this realm, white holes, those hypothetical, opposite counterparts to black holes, offer an intriguing possibility. Could they be gateways to time travel? In classical physics, time is considered to be an unyielding, one-way flow. But when we enter the world of general relativity and quantum mechanics, time becomes much more malleable. In fact, both theories suggest that time is intimately connected with the fabric of space-time itself. Space-time can be warped and bent by the presence of massive objects, and this warping can affect the passage of time. For example, near a black hole, time passes more slowly for an object closer to the event horizon compared to one further away. This concept of gravitational time dilation suggests that time is not fixed and uniform throughout the universe, but rather it can stretch and shrink depending on the forces at play. Now, consider white holes in this context. While black holes trap everything that falls into them, white holes are theorized to do the opposite. They expel matter and energy, never allowing anything to enter. This characteristic of white holes raises an intriguing question. Could these cosmic objects function as time portals? If a white hole exists in a region of space-time where the flow of time is reversed or significantly altered, could it provide a means to travel backward in time or into the distant future? Some speculative theories suggest that white holes could be the result of time anomalies, functioning like openings in the fabric of space-time. These openings could provide a passage from one point in time to another, much like a wormhole, which is another theoretical construct in general relativity. If white holes are connected to the past or future in some way, they might offer a mechanism for traveling through time. Imagine being able to step into a white hole and emerge in a different era, whether in the past, where you could witness ancient civilizations, or into the future, where the universe's mysteries might be revealed. Of course, this is all purely theoretical, and the challenges of time travel, if it is even possible, are enormous. The very existence of white holes remains uncertain, and even if they do exist, we have no idea how they would work or how we might harness them for time travel. Yet the idea of using a white hole to travel through time opens up a fascinating line of inquiry, one that blends the most advanced concepts of physics with the timeless human fascination with altering time itself. Take a moment to reflect on this. If white holes are truly connected to time in some way, what would it mean for our understanding of the universe? Could time travel, once thought to be the stuff of fantasy, be possible through the expulsion of energy from a white hole? As we explore these possibilities, we find that the line between science fiction and science reality grows ever more blurred, inviting us to reconsider our most fundamental assumptions about time and existence. The concept of time travel often brings to mind images of heroic adventures, futuristic technology, and the chance to undo past mistakes or glimpse the future. But as with any powerful tool or ability, time travel raises profound ethical questions. If time travel were possible, what responsibilities would come with it? Would it be right to travel back and alter the past, potentially changing the course of history? Or would it be wiser to view the future with caution, knowing that seeing what lies ahead could alter the decisions of the present in ways we cannot fully anticipate? The ethical implications of time travel are not only complex, but deeply intertwined with the very essence of human choices, responsibility, and the nature of existence. At its core, time travel presents a moral dilemma. One of the most significant questions concerns whether it is right to intervene in the past. Consider the idea of going back in time to prevent a tragedy, a war, an accident, or even the death of a loved one. On one hand, the desire to correct past mistakes or save lives is a deeply human instinct, driven by empathy and compassion. Yet, altering the past could have unintended consequences, disrupting the delicate fabric of events that followed. This is famously known as the butterfly effect. The idea that even small changes in the past could lead to massive, unpredictable consequences in the future. A single decision to change history could lead to an entirely different present, one that might not be better and could even be worse. So the question becomes, should we tamper with the past, knowing the risks of potentially catastrophic outcomes? This leads to another ethical dilemma: the power of knowledge about the future. What if we could travel ahead in time and witness future events? Would knowing the outcome of our decisions diminish our free will, knowing that the future is already set? Or would it offer us a moral responsibility to make different choices based on what we know lies ahead? The very act of knowing the future could fundamentally alter how we approach our present decisions. It could make us more cautious, more proactive, or perhaps even more reckless, depending on what we discover. Would the future's outcomes truly be set in stone? Or would our knowledge and actions now serve to reshape it? In the case of white holes, which may theoretically expel matter and energy from a previous universe or cycle, the ethical concerns become even more abstract. If these cosmic entities are involved in creating new universes or new timelines, could the actions of those within one universe, like us, influence the creation of another? Is it ethical to potentially create or destroy entire realms of existence? While this is still far beyond our reach, such philosophical questions challenge us to consider not just our own universe, but the potential consequences of all possible realities. Take a moment to reflect on this. The allure of time travel, while filled with possibilities, brings with it heavy moral responsibility. If we could alter the past or peer into the future, how would we use this power? The ethics of time travel are not just theoretical. They speak to our deepest values and desires, forcing us to confront the ways in which we shape our present and future, both for ourselves and for all of existence. Quantum mechanics is a realm that defies intuition, where particles can exist in multiple states simultaneously and events unfold with an inherent unpredictability. At the heart of quantum mechanics lies the concept of quantum fluctuations, tiny, momentary changes in energy that occur even in seemingly empty space. These fluctuations are not random in a simple sense. They are a result of the uncertainty principle, which asserts that the precise state of a particle, such as its position and momentum, cannot be known simultaneously with perfect accuracy. This inherent uncertainty in the quantum world leads to the appearance and disappearance of particles, creating what we call quantum foam, a turbulent, fluctuating field of energy at the smallest scales of space and time. But could these quantum fluctuations play a role in the creation of white holes, and perhaps even the entire universe itself? One theory suggests that the Big Bang, the origin of our universe, could have been the result of a quantum fluctuation in a pre-existing vacuum. In this view, a region of space could have experienced a fluctuation so large that it birthed all the matter and energy in the universe, triggering an expansion that continues to this day. The fluctuation would have provided the necessary energy to overcome the constraints of the vacuum, causing space-time to stretch and create a new cosmos. This idea ties into the broader concept of cosmic inflation, where the universe rapidly expanded from a singular, infinitesimally small point into the vast space we observe today. But quantum fluctuations may not just explain the birth of the universe. They may also provide a possible link to white holes. If we consider a white hole as a cosmic entity that expels matter and energy into the universe, could it be the result of an extreme fluctuation in the quantum field? In this model, a white hole might be formed when a large fluctuation of energy leads to a rapid expansion of space and time, pushing matter and energy out into the cosmos. Rather than pulling matter in, as a black hole does, a white hole would do the opposite, expelling energy and matter, potentially even creating new universes or timelines in the process. The link between quantum fluctuations and white holes leads to an intriguing possibility that both the birth of our universe and the creation of white holes could be tied to the same quantum phenomena. These fluctuations, though invisible to us, could be the underlying mechanism that drives both the expansion of space-time and the creation of matter. If white holes are the result of such fluctuations, they may represent not just a theoretical curiosity, but a fundamental part of the universe's ongoing creation and evolution. Take a moment to reflect on this idea. If quantum fluctuations are responsible for the creation of white holes, and by extension the universe itself, then the very nature of existence may be far more deeply connected to the quantum world than we ever imagined. Could the universe's continual expansion and the potential birth of new white holes be part of an ongoing cycle of creation governed by the mysterious forces of quantum mechanics? This concept invites us to rethink not just the origins of our universe, but the deeper, hidden processes that drive the cosmos forward. The pursuit of knowledge has been a defining characteristic of humanity for as long as we have existed. From the earliest days of civilization, when humans first gazed up at the night sky, wondering what lay beyond, to modern times, when we probe the deepest corners of the universe with advanced telescopes and particle accelerators. Our quest to understand the cosmos has never waned. This journey for understanding is not just about accumulating facts or discovering new phenomena. It's about trying to grasp the larger meaning of existence, the place of humanity in the vast expanse of time and space, and perhaps even the very nature of reality itself. The search for knowledge is infinite in nature, much like the universe itself. Every discovery brings new questions, opening doors to further mysteries and deeper inquiries. Take the concept of the Big Bang, for example. For decades, it was the definitive explanation for the origin of the universe. It was thought to be the ultimate beginning, an event from which everything we know emerged. Yet, as we delve deeper into this theory, we encounter even more complex and fascinating questions. What triggered the Big Bang? Was it the first event or part of an eternal cycle of creation and destruction? What happened before the Big Bang? Or was time itself born with it? These questions don't detract from the significance of the Big Bang theory. They enhance it, opening up new avenues for exploration and contemplation. Similarly, the notion of white holes, objects that are theoretical opposites of black holes, challenges our understanding of physics and the fabric of space-time. While black holes are fascinating in their own right, white holes push the boundaries of what we know about the universe. If black holes trap everything that falls into them, then white holes might expel everything, potentially creating new matter or even whole universes. This idea not only deepens our understanding of cosmic phenomena, but also forces us to rethink the fundamental laws of physics. How do objects like black holes and white holes fit into the larger framework of our universe? And if white holes exist, could they be the key to understanding the cyclical nature of cosmic creation and destruction? Take a moment to reflect on this. The infinite quest for knowledge is not just about finding answers. It's about embracing the mysteries and the unknowns of the universe. The more we learn, the more we realize how little we truly understand. And yet, that very realization is what drives us forward. Each new discovery is a step in an endless journey of exploration, challenging us to expand the boundaries of what we know and to confront the profound questions about our place in the cosmos. As we look up at the stars, we are not only seeking answers about the universe, we are seeking answers about ourselves, about the nature of existence, and about the infinite possibilities that lie ahead.